welcome. My name is Oleksandr Chaban, a PhD student at Khmelnytsky National University, and I'm honored to present our research co-authored with Professor Eduard Mandzuk. Today, we'll be discussing how we enhance medical natural language interface, or NLI, by integrating domain knowledge and sentiment analysis. This work is a part of a broader effort to improve clinical decision-making by integrating medical domain knowledge using AI. Medical NLI is crucial in healthcare for interpreting clinical notes and improving automated decision-making. But the challenge lies in the complexity of medical language, terms and context that differ vastly from general domains. Our work aims to address these challenges by enhancing NLI models with two key elements: domain knowledge for medical ontologies, like UMLS, and sentiment analysis tailored for clinical texts. We believe that this integration will make AI system more reliable for tasks like medical record and analysis and decision support. In this slide, I will outline the main goals of our approach. First, we aim to enhance NLI models by embedding domain-specific knowledge from sources like UMLS, which stands for the Unified Medical Language System. UMLS helps the model understand complex medical terms. Second, we add sentiment analysis to help models interpret the emotional tone of medical notes. For example, detecting when a phrase like "no signs of infection" indicates a positive outcome. Finally, we evaluated our approach using the MedNLI dataset and compared our model performance with existing models. Our goal is to improve NLI accuracy, precision, recall, and other performance metrics. Let's now move to the technical part. Our approach combines two state-of-the-art models: BioELMO for generating contextual word embeddings, and Multi-E for embedding domain knowledge from UMLS. As you can see in the diagram, we start by tokenizing clinical text, extracting UMLS concepts, and applying sentiment analysis. Then we generate embeddings for both domain knowledge and sentiment, which are passed through a deep learning architecture for classification. Our key innovation here is the way we merge contextual embedding with domain-specific knowledge and sentiment, which improves the model's ability to understand clinical language. Here we dive deeper into how we combine different types of embeddings. First, we use BioELMO, which generates contextual embeddings from large medical corpora like PubMed. Then we incorporate Multi-E embeddings for domain knowledge from UMLS. We also add sentiment information to each word. For example, in clinical notes, phrases that mention pain or illness would be flagged as negative, while those indicating improvement are positive. The final representation is a weighted sum of these embeddings with attention mechanism to prioritize important terms. Now let's focus on the Multi-E embeddings. The Multi-E model represents medical concepts as vectors. These concepts, extracted from UMLS, are embedded based on their relationship with each other, whether they are symptoms, diagnosis, treatments, etc. We use a special non-linear transformation to capture complex relationship between medical terms. This helps the model to not just recognize medical jargon, but understand how these terms relate in the real world, such as linking COPD to chronic obstructive pulmonary disease. By doing this, we give the model a deeper understanding of medical language. In this slide, we explain how we represent each word. Each word in the clinical notes get three types of embeddings: a contextual embedding from BO-ELMO, a domain knowledge embedding from multi-E, and the sentiment vector. These embeddings are then combined using a weighted sum approach, meaning that the model learns which type of embeddings is most important for each word in a given context. For instance, in clinical sentences, where sentiment is critical, the sentiment vector might have more weight than the domain knowledge. The attention mechanism we employ ensures the model focuses on the most relevant parts of the sentence. Now let's look at the results. This table shows how our proposed approach compares with other models in the meta-NLI dataset. You can see that our model outperforms the baseline in every category: accuracy, precision, recall, F1 score, and AUC, ROC. For example, traditional fast text achieves an accuracy of 73.5%, while our model reaches 81.14%. Even BO-ELMO with sentiment analysis falls short of our method. The integration of domain knowledge and sentiment analysis really boosts the model ability to handle complex clinical text, significantly improving its performance. To summarize those results, we see that the sentiment analysis, when integrated with medical domain knowledge, provides a substantial edge in classifying medical text. Our method effectively reduces false positives and false negatives, making it more reliable for real-world application in healthcare. These performance improvements show that models, when equipped with both medical knowledge and sentiment understanding, can deliver better predictions, which is crucial in clinical decision making. In conclusion, our approach combining domain knowledge from UMLS with sentiment analysis improves the accuracy of medical NLI tasks. Our model achieves superior results across all key metrics: accuracy, precision, recall, F1 score, and AUC, ROC. This work demonstrates the importance of incorporating domain-specific knowledge and sentiment in medical AI. However, we recognize there are still challenges, especially in refining sentiment detection and processing time-sensitive clinical information. Looking ahead, we plan to focus on improving the model's ability to interpret more subtle sentiments and handle temporal data, which will further enhance its real-world applicability in healthcare. Thank you for your attention. I'm happy to answer any questions.